Thank you for the nice introduction. It is indeed work that has something to do with the last year CosmWasm. It's not the same, but what it is really about, you'll find out. Thanks for coming to the workshop. I hope you're having great hackathon so far, and enjoy lunch as well. And I'm looking forward to working with you in the next couple of days. I know some of you from today morning. For the rest of you, my name is Ivan. I'm from Informal Systems, and I would like to talk to you about one thing that is important for all of us, and this is how do we know that our contracts that we write are secure and correct? And we are a rather small group, so let's just feel free to interrupt, discuss, and generally be a bit more relaxed in this workshop so that it does not have to be slide after slide. I'm basing this workshop on our experience in Informal in the last couple of years working on security. And this experience can be summarized in the title of this talk, which is Practical Formal Methods with Quint. What do I mean by that? So, formal methods is a discipline of computer science that let us prove properties about our programs. So that's amazing. Why not just everybody use formal methods? However, very few people actually do use formal methods. And there is a very good reason for that. It is because they're very expensive to use. If you want to do hardcore proof that your contract or that your program is correct, you can easily count on 1 or 2 years of dedicated expert working only on that. And while this is a good idea if you're launching a spaceship or if you're building a verified kernel, for majority of software projects, just is not viable. And people in this community noticed that, so they started to work on more and more practical formal methods, kind of trading off a bit of rigor for practicality. And our contribution at Informal was by building Quint. We like to refer to it as a delightful modeling language that brings formal methods to practice. And I will go more into detail what I mean by that. But first, our goals for today. It's a short workshop, and we have modest goals, 3 goals. First, I would like us all to try out Quint. If you have your laptops ready, that would be amazing. I sent a message on installation instructions. If you didn't follow, it's just one command. But even without your laptops ready, you will be able to follow along in the workshop. So choose your way of following. So the first goal was to try out Quint. The second goal was to actually see Quint in action, see how we can use Quint to find bugs in a CosmWasm contract. And finally, as the last thing of the workshop, I would like to show you some recent developments which connect CosmWasm to Quint, what Simon was referring to. And Quint is a general purpose modeling language, but if you are to use it with CosmWasm, we have some tooling that will make it even easier to be used. Okay, throughout the workshop, throughout the hackathon, my colleague Philip is here in the audience. So if you would like to experiment with Quint later in your hackathon projects or have questions now, just ask Philip or ask me. We are very eager to help and assist with Quint during this hackathon. Let's start with what Quint is, how it works. I use this somewhat weird and non-technical term, a delightful modeling language. So what is a modeling language? It is a way to capture essential properties of our program, but on a more abstract level. And then modeling language comes with the engine to reason, to prove properties of the model. What is an example of being more abstract? Let's say you are implementing a distributed systems. So you're interested in different nodes communicating, crashing, recovering, but you don't care about the individual memory allocations on each of them, something like that. So you would just model these important properties. And there were modeling languages before Quint, of course, but because formal methods was a fringe discipline for a long time, they do not cater toward general developers, but rather to formal methods experts. And that's why they look like a big mathematical formula. They are not really easy to use, and they're not integrated into development process. That's why our goal with Quint was always to make it a delight to use, first to use familiar programming conventions, and then to have it integrated in the development cycle. This is not only nice and comfortable to use, this also helps with one very important problem, and this is a divergence between code and the model. Let's say you once write a model, and then the implementation diverges from it. With Quint, we can generate many tests from the model that then keep the model and the implementation in sync. So this is one of the advantages of having a delightful modeling language. And here, I'm not talking only about our goals, but really about our experience with Quint. I personally work in the informal security branch, where we do security audits for projects across the ecosystem. One recent example was that we worked on an audit of a Neutron smart contracts in CosmWasm. And together with the Neutron development team, we managed to model it with Quint, find bugs, and fix them before going live, which is the whole point of security audits. And not always, but very often in audits, we would use Quint. More broadly than security audits at Informal, we use Quint for designing critical protocols. Philip here, whom I mentioned, he is working in Cosmos Hub team, and they used Quint for modeling partial set security. Okay, very good. So far we have said what are the goals with Quint, what are these properties, but I think we will all get the idea what Quint is once we try it out. And let's try it out on a toy example. Here's a protocol that I call Safe Zone protocol, which only has one state variable, which is x, and its initial value is 21. And then there are users who can interact with the protocol by sending message, be it up with parameter force, and upon receiving this message, the protocol increases the value of x, and I'm using x prime as the next value of x, increases it by 6 times force. Or users can send down force, and then this decreases the value by 9 times force, with additional quirk that it only happens if the new value is not going to be negative. And let's say that for whatever reason, if x ever reaches 0, an exploit is possible. So the question for us is our protocol safe? Is an exploit possible here? So maybe some of you see it mathematically, but let's see how we would go about this, model it in Quint. Okay, so here is our very basic Quint model. And basically, in order to model things with Quint, we need to do 4 things. First one is defining what are our state variables. So this one is easy. We say var x of type integer. We have that. Then we will need to define initial state, but let me skip this for a second. I'll get back to it. Then we will need to define users' messages, so up and down. And in the Quint terminology, a user message is an action, changing state from one to another. So I'm saying action up, which receive force, and let me remind myself, so this was x plus 6 times force. So x prime becomes x plus 6 times force. Very good, that's it, we have modeled the up. Now let me get back to the init message. So basically we want to say that x is 21, but in Quint, initialization is also an action. It is an action from a non-existent state to the initial state. So similarly here, I'm going to use a customary name init, action init, and I'm going to say x prime equals 21. Why x prime? Because this is a transition from a non-existent state to an initial state. Therefore, the next value of x, 21, this is the initialization. Okay, and now we need to write action down as well. So is anybody following along on the laptop? No? No. Okay, then let me do that. So action down, also with force. Well, it would be basically the same as up, except for this additional quirk that it cannot go negative. So we want to model that as well. So we say that x minus 9 times force is always greater than or equal than 0. And I have immediately the editor complaining about the syntax. So we have given 2 conditions, 2 relations, but we did not say how they relate to each other. So we want that both of these are satisfied. So in Quint, we would use all to denote that all of these need to be true. Okay. Basically, if you're wondering about the different things for Quint, there is a cheat sheet. And in the repo to this document, I have links to that. What are the different syntaxes of Quint? We'll get back to it later on as well. Okay, so very much now, we have defined some parts of the model. We're still missing model evolution, but I would like to show you that with Quint, even when your models are only partially developed, you can check them and see how they work, whether we did right thing or not. So we would say something like Quint and then require that it loads the safe zone, module safe zone. And here we can ask, okay, what is x? And it will say x is an integer variable, but it's not initialized yet, which makes sense. It indeed is not initialized. If we run action in it, it will say true, action succeeded, and x is now 21. And then we can say, for example, up with force 2, and x is now 33. Or we can try to say down with force 7, but now it will say false. Why? Because we required both to be true. So this condition was not satisfied. Therefore, the down thing could not happen. And we can still play a bit with the REPL, up, down, whatever. And we see somehow that x is never 0. So perhaps our protocol is correct. But let's not hope for that. Let's prove that it's correct. So we have to define how does our model evolve. It is again another action which is customary called step. And for us, this is users either send up force or down force. Since it is either, we use any keyword. So it's either up force or it's a down force. And you will see it again complains what is force. Well, force is a user supplied value. There are different users, they can choose at different time points, different values for force. So from the perspective of the model, we don't know what is force. It is a non-deterministic value. We do not choose them. And in Quint, we have to be explicit about when we are using a non-deterministic value. So we say non-det force equals 1 of, and you will see the helper saying that 1 of provided a set, and then it will choose any of this set. And it will make sure that any properties you prove are true for any of the set. So here I will use 1 to 100. Let's assume that users can only set to 100 for being faster, but any set would do here. Okay, and now we have defined the whole model. We can simulate it, we can run it, and we are interested in some properties. Here, for our case, we are interested if x is ever going to reach 0. So let's see that. We just define these properties and let's call it safe, because this is safe for us, and we are safe if it's not the case that x ever equals 0. And now, because we have it in the modeling language, we can verify whether it's true. In Quint, we do this verification under quotations in two ways, either by running simulation or by doing proper verification. So if I do Quint run, this is going to run a number of simulations to see whether the property is going to be violated. So I'm going to specify that my invariant, I'm saying this is invariant. Invariant means a property that needs to hold across all states of the evolution. So I say, make sure that this property holds, property safe, and find me if there's a counterexample. And immediately we get, oh yeah, there is a counterexample. And here's one counterexample. And we can also, providing additional flag, we can get a bit more data on how this property was. So this is a bit of an involved thing. And you notice that last time the counterexample had 5 or 6 steps. Now it has 13. This is because this simulations is not deterministic runs, so every time you will get a different result. So our protocol was not safe. Violation is possible. I am suggesting here that we will fix our protocol if we say x equals 20, and then it will be fine. But don't trust me, let's verify that. We can again run this simulation. It will take some time now. And let's hope that it is correct this time. Oh, it is correct. It says no violation found. But can we really trust that it's correct? It just ran number of simulations, so we cannot trust it is correct. It is very likely correct, but we are not sure. That's why Quint has another one, which is called Quint Verify. And this one is really gonna verify. There is a caveat up to a certain number of steps, but for this certain number of steps, it's gonna make sure that for all possible values of force and all possible reorderings of up and down, there will be no violation. Let's try that. Invariant is safe zone. Here, it is not gonna last for too long, but the typical trade-off between whether you wanna use verify or run is that verify is typically slower. So sometimes it can take hours for complicated protocols, whereas simulation is always fast. So it's a trade-off you get to choose from. Okay, so we have now seen if we have a protocol idea, we model it a Quint, we can see whether it's correct or not. Very good. Let's get back to CosmWasm. The second talk would be, now we have an idea of Quint, but how do we use Quint to find bugs in a CosmWasm contract? In principle, there are two ways to do so. The first one is by generating a large number of tests from model simulation. So typical workflow would be that we have an idea or English specification, and then we model it in Quint. And from Quint evolution, we generate many traces, and then run those traces against the code, and then look for bugs. How do we look for bugs? We compare the output of the tests with the output from the model. If they do not match, something is broken. The other approach is that we verify the model. In that case, we have to go from the code to Quint, and then verify properties of Quint to find bugs. How do these two approaches compare? Well, the left-hand side can be as abstract as you wish. It can model only some parts or all parts, as long as you can run meaningful tests from them, whereas the right-hand side needs to be very close to the code. And then, so typically, right-hand side is going to be a bit larger. And I'm going to show finding bugs in CosmWasm on the capture the flag from the last year's AwesomWasm. This was organized by Oak Security, our colleagues. It was a good challenge, so kudos to colleagues. If you remember or don't, I'm going to introduce the protocol shortly. There were some lockups, and users were able to deposit to the contract, upon which new lockups was added. This plus is not numerical plus, it just adds to the set of lockups. Or withdraw, upon which lockups were taken out under the condition that the sender owns all of these IDs from the list and the lockup period is over. And then the question is it possible for a user to drain the contract? Now, of course, this was a challenge in the capture the flag competition. Of course, it was possible, but how is it possible and how do we use Quint to do this? Let's find out. So again, here, we would go and model the code as we did with the safe zone, following the idea. And here I'm not gonna go into all the detail, but just show you that when I did the modeling, it follows the same structure as with the safe zone protocol. The definition of variables, the initial state, the evolution, and all the actions. And you will notice here, beside the deposit and withdraw actions, which are users' actions, there's also advanced time period, because for this contract, it matters what is the time. Okay, so now we have this contract written, and you will, by the way, you can find it in the repo about this workshop. I sent it to Telegram. I can send it again if you're interested. And we can just say Quint run. So give us some number of simulations. Let's say 100, and run idea guided. I'm calling it idea guided because it does not stem from the code, but from the idea of the code. Okay, and it runs now. It shows me one of these samples, but it generates more of them. And it generates it in the machine readable form in the JSON. We also have a plugin which is called ITF Trace Viewer, which shows it also in human readable form. So to show what the sample was about, you know, first advanced time, then deposit again, then advanced time, and so on and so forth. Okay, now that we have all these traces, we can use them to generate tests. So how does a test look like? It iterates over all the traces that we have generated, and then inside the single trace, it iterates over all the states, and then uses CW multitest to execute those messages. And in the end, it compares states. So if we run this test, okay, for whatever reason, it does not run. Wait a second. Okay, the test fails. And how does it fail? Let's inspect. It fails here. It says there was a user that withdrew and it supplied the list 333. So something is weird here. It supplied lists with all the same IDs. And you know, it may be an actual bug or it may be just an artifact of our modeling. So let's see in the code. I don't know if you remember this challenge. But if you see in the code what was happening here, the code was just iterating over all the IDs supplied by the user. It was checking for the owner, it was checking for the block time, but it never checked for duplicates. So indeed, this is the way to drain the contract. And by generating 100 now, but in principle thousands or tens of thousands of tests, we covered this edge case and we found it here. Okay, very good. And now to the third part. Yep. Mm-hmm. What I showed you now is not more smart than that. But in general, using Quint for that is smarter because of two reasons mainly. One is that you can define these invariants, or they're similar to invariants, but they're called witnesses, where you can describe interesting behaviors you want to see. And you're not describing them step by step, but you say just what is the end state of this behavior, and you let the Quint figure out how to reach this interesting behavior. So that's one thing. And the other thing is that if you're using separate Quint simulator, you benefit from all the development in the simulator that is independent of other parts of the testing suite. So it's kind of this writing tests where the data is separated from the execution. That's the idea. Okay. Good. So in this last part of the workshop, I would like to show you these recent developments with some CosmWasm specific tooling. And we talked about two ways of generating bugs. One was to generate tests, and the other one is to verify the model. And in verifying the model, we said we are starting from the code, we write the Quint spec, and then we find bugs by running verification. The problem here is the constructs are typically larger than the models, and if you want to write a model that closely follows the construct, it's going to be quite a large model. So some of you may ask, is it worth it? Is it worth writing again the construct, but just now in Quint? And the second question is, how can we be sure that we will find some bugs in Quint, but maybe we made a mistake writing the model, so we are going to actually find bugs in the model that do not exist in the code? And to answer these both questions, we have developed a thing called CosmWasm to Quint. So here's this repository. It's public from yesterday evening. It's a very, it's complete thing, not beta tested yet, but complete. And what it can do for us. Let's see it. Oh, basically, I think I skipped one slide where I show what it can do for us. Yes. Sorry, skip the part. What we do here is we use the Rust compilation process where we get into the Rust compiler and get all the information about key parts of the construct, translate it to Quint automatically, and we do everything but a small business logic part. So this makes it, first makes it more reliable that we did not make a mistake, and second, makes it easier for us because now we have to write in Quint only a smaller part. Let's see it on the example. So if we go here, so we are now in the CTF01, so this is this challenge thing, and we run cargo CosmWasm to Quint, and before that we have to clean because compilation needs to happen for us to get into it. It is now analyzing all the parts, and it generates a stub. And the stub it generated is here. So you will see that it generates a lot of this, what would be called a boilerplate, what is an obstacle to start working with something meaningful, and it will generate these deposit and withdraw functions. Well, it will tell you, okay, this is to do, specify the logic here. For now, it is going to say, I'm not going to modify the state, but it's up to you to say what to do here. And when you see, so I filled it in here. If you want to see how it looks like when it's added, here. So we are talking about roughly 20 lines of code. So now model. So now you go from writing 200 lines of model to writing 20 lines of model that is similar to what you've seen in the contract code. Of course, it's a different syntax, but roughly you're following the same logic. And now that we have that, we can verify this model that we have generated. So I'm going to do Quint run. Okay, but what is the property we would like to check for? So here, if you remember, what was important for us that the user is not draining a contract. What does it mean to drain a contract? So here's the property I define. We want that the contract address has more funds than it had initially. And we want this to always be the case, more or equal to. Because if it has less, it means some user is draining funds. And the property name is contract balance OK. So now I'm going to do Quint run, invariant. And this one is called code guided because it is inspired by the implementation, and then the model was written. And we immediately found an issue. It tells us the invariant is violated, and we see again that it actually found the same root cause issue, that the identifier was repeated here in the list. Okay, so very good. Again, as I said, if you want to find out about this thing, it is here, and because this is a bit of shorter workshop, we also added a file that tells how to, in the workshop material, we added the file that tells how to go over all the steps of generating and what things to change and trial and error and what happens there, which is necessary in this kind of iterative process. Okay. Good. So this is the repo. And one more thing, it's a product of a recent internship we had at Informal, where we in the previous one we had to write business logic ourselves, and here we tried AI generation of model business logic. And so what we did is we gave either the code or the user input, depending on what we had, on what is the workflow, and asked a large language model to generate the code. But the important point here is that we do not accept the LLM's output blindly. We have to ground it somehow. And we do it using this triangle of trust, where input-output examples, and then the generated code and tests, or available code and generated tests, and the generated model need all to be mutually consistent. And when they are consistent, then we propose a solution, we give it to the user to verify the generated model. So this one is still immature, still is being worked on, but expect something coming from that soon enough. Okay, to follow these developments, here's a model-based techniques web that we have. Then there's a Quint language Telegram group where there's the Quint core development team. If you have questions, you ask, and then they try to help. And finally, Informal's blog. I would really like to encourage you to try out Quint. It's delightful. And in these 2 days, Philip and I are around to help you and answer all the questions. So in this workshop, we show how to use Quint before and after implementing CosmWasm contract. Before, if you have an idea, so for example, here in the hackathon, you sketch a protocol on the whiteboard. Forget about whiteboard, sketch the protocol in Quint and have properties of it proven immediately. And then for after, you can either verify the contract, find bugs, or produce a large number of tests for your CosmWasm contract. So let's talk after this workshop. If you have questions about the contact, if you want to discuss your project, be it the hackathon project or one that you're working on as part of your work, if you need a security audit, or if you need help designing or implementing distributed protocols, this is all what we at Informal do and can help with. If you want to get a beer together in the next 2 days, let's talk. Or if you want to work with us on Quint, let's talk too. So now I'm open to any questions, discussions, and comments. Thank you for your attention, and thanks for coming here after lunch.